Welcome. We will look on the last problem number 5, which is very applicable. It's about counting strings which avoid a certain pattern. So let us consider strings made of 3 letters ABC. That means strings over the alphabet ABC. And for n 0 or bigger, that will be the length of the strings. S sub n will be the number of strings over this alphabet ABC of length n, which don't contain the pattern AA. Alright, so to get a feeling for the problem, first we are asked to find S0, S1, S2, S3. Especially S3 it's a good special case which reveals actually the general method for the counting. And then in the second part, in part B, we are supposed to find a recurrence relation for the sequence S0, S1, S2. That's typical the approach for these kinds of problems. It's much easier to find a recurrence relation for Sn and then to solve it algebraically than necessarily look directly for the formula for Sn. Alright, so for part A, S0 is 1. Why? Because we have the null string of length 0, so that's that one string. S1 is 3 because we have strings ABC. S2 is 8, and I listed all the 8 strings which have 2 symbols but no AA, so AA is missing on that list. S3 is 22. Why? And that's the most important case in this first part, because I will argue the same way as in the general case. So let us look on strings of length 3 which don't contain AA, and let us divide the counting by the starting letter in the string. If the string starts with B, we have 2 letters to fill out after that, and no AA is allowed, so we have S sub 2 options. All the strings of length 2 which don't contain AA can be in those 2 slots. If our string starts with C, we have again S sub 2 options, same type of argument. On the other hand, if the string starts with A, we cannot just put a string without AA, for example, on the next 2 slots. For example, if we put A and then a string AB, we will create the repeating pattern AA. So we need to go a little bit further. So if the string starts with A, we need to distinguish whether the next letter is B or C. A is not allowed as the second letter. If the second letter is either B or C, the third letter, we can use any of the 3 options we have, A, B, and C. So altogether, counting what we got, we have 8, that's S sub 2, 8 plus 8 plus 3 plus 3, that's 22 strings. So 22 strings of length 3 don't have repeating AA. So now with this, let us look on the general case. S sub n will be number of strings, length n, no AA, and we will count such strings based on the starting letter. So if the starting letter is A, then we need to follow by B or C, and then we are left with filling up n-2 letters, because 2 are already filled up, either AB or AC. And on the n-2 we can put any string of length n-2 which has no repeating AA, and there is Sn-2 such options in both cases. If the string starts with B or C, then after B or C we can put any strings of length n-1 where we don't repeat AA. We have a name for number of such strings, that's Sn minus 1 in both cases. So altogether we have that Sn is 2 Sn minus 1 plus 2 Sn minus 2, counting all the cases. And from the part A we know that S0 is 1, S2 is 3, and that's the answer for part B. That's the recursive relation with the initial conditions needed. And that's the whole solution of problem 5. Thank you.